So let's talk about titrations and titration curves. So you'll spend a lot of time in labs doing titrations. So what a titration is you would have a burette, and you'll have a much better drawings of this with your lab materials. But what is in the burette is called the titrant. This is what you are adding in. And then you have you're usually trying to figure out some unknown concentration. Either you don't know the concentration of the titrant that's in your burette, or you don't know the concentration of what is in your flask, which is called the analyte. So you add in a volume of titrant, and then you add it in until you reach what's called the equivalence point. And the equivalence point, you are able to determine what the equivalence point is because it goes from a colorless liquid to the faintest pink color that you can see. It should be just barely colorless. If it's bright pink like this, then you know you've way over titrated. You've added way too much because you're going to add an indicator called phenolphthalein for your labs, and it will tell you when you've reached the end point. So the end point is when you have equimolar of whatever is reacting. In our case, it's going to be acids and bases. So we are going to plot out the change in pH of this analyte. So in lab, you would have a pH probe in this analyte, in this solution down here, and as you add the titrant in, the pH is going to change. So let's just say, for example, that in our titrant up here in the burette, we have sodium hydroxide, and in our analyte down here in the flask, we have acetic acid, which, again, the formula isn't important. It's just HA. It's a weak acid. So we're titrating a strong base with a weak acid. The equivalence point is when we have equimolar concentrations of acid and base. So equal amounts. So we are going to be collecting data on a graph as these reactions are happening, and it will look something like this. And as we continue to add volume of titrant, the pH will increase because the pH is going to increase as you add base to this analyte. And depending on what the Ka of acetic acid is, that's where you'll start in all of this. So what's important in this titration curve is this region right here where you are continuing to add this base, but you see the pH isn't really changing. This is called the buffering region. Halfway through the buffering region, let's say if this was the buffering region right here, halfway through the buffering region, this is called the half equivalence point. Equivalence, I'll write out equivalence point. And here, where it is totally vertical, halfway through this vertical part, we'll say right here, this is called the equivalence point. So you're going to have seen all of this in lab. There will be animations and simulations for you to go through and virtually add titrant to this analyte and kind of see how this graph is produced. We're going to talk about some of the calculations here. So the buffering region down here is where we are adding base and the buffer is able to not allow the pH to change. So that's the job of a buffer, is that it resists change in pH even though we're adding volume. So whatever this measure of volume is, however many milliliters of sodium hydroxide we've added, this buffer is resisting change in pH. Once you exceed the capacity of this buffer, the pH is going to go up pretty quickly because we're outside of the buffering range, and now with just a small volume of sodium hydroxide, the pH is going to go way up. So up here at the equivalence point, this is where we have equimolar concentration of whatever is reacting. So it's going to be hydronium and hydroxide, in this case, the hydronium from the acetic acid and the hydroxide from the titrant. So when this is equal, then you have reached the equivalence point, when you have equimolar concentrations of acids and bases. So we're going to be doing a calculation of a weak acid and a strong base titration problem, and then we are going to draw our own titration curve. So this video is just to kind of introduce what titrations are and what titration curves tell us, and then we're going to do a 5-step problem calculating the following. So we're going to do a weak acid and strong base titration. So we're going to do this. We're going to say find the pH at each of the following points. In the titration, of 25 milliliters of 0.30 molar hydrogen fluoride with 0.30 molar sodium hydroxide. And then the Ka of hydrogen fluoride is 6.6 times 10 to the negative 4th. So first is going to be the initial pH. So this is before any titrant is added. So we're solving for the pH inside this flask. The next point is going to be after adding 10 milliliters of titrant, sodium hydroxide. The third point is going to be after adding 12.50 milliliters of sodium hydroxide. The fourth point is going to be after adding 25 milliliters of sodium hydroxide. And then the fifth is going to be after adding 26 milliliters of sodium hydroxide. So we're going to do this 5-step problem. I'll probably do one video for each step, and we're going to draw our own titration curve at the end after we've determined what the pH is after adding each of these volumes of sodium hydroxide into, here my example was acetic acid, but what we're actually going to be using is hydrofluoric acid. It doesn't really matter which acid it is as long as it's a weak acid. So this is kind of introducing what we're going to be doing in the next few videos. This is a weak acid and a strong base titration.